Alright, good morning. So we're going to be going over the third lesson of energy called Simple Machines, Mechanical Advantage, and Efficiency. So our first lesson we went over work and power. Kind of work is showing the amount of joules you perform a force over a certain distance. And then we went to a second lesson looking at these joules of energy working for kinetic and potential energy. And how to do certain questions with that. And then this next one we're going to be looking into simple machines and how they can have a mechanical advantage and an efficiency with them. So overall we should all know that there's 6 simple machines: the screw, the wedge, the ramp, the pulley, the lever, and the wheel and axle. Okay, so we have a wheel and an axle. We got the lever that has a fulcrum with it. We have a pulley with a rope generally. We have a ramp. We've done questions with ramps before. We have a wedge, which is usually like an axe. To be honest, the simple machines, the wedge and the screw version, we don't really look at all. But they're still examples of simple machines. Some sort of screw. Alright, so we have those 6 examples. What we really look at is these 4. We don't really look at wedge and screw because they're a little too, I guess, complicated. And they're really just examples of special types of ramps anyways. So it's really these 4 examples. Okay, so these are all machines that make it easier to lift and move things against a force. So generally we use these simple machines to make things easier to lift. Okay, so if you have a 500 kilogram object, you're not going to try to lift it up 1 meter. You might have to use certain simple machines to help you do that. So working against the force. For example, a pulley might make it 2 times easier to lift a box. Does it? And then the next question I have here is, does it reduce the amount of work to lift though? So let's explore that through this sample. A box has a force of gravity of 100 newtons. Which means the mass would be around 10 kilograms, because 10 times 9.81 would give us around this. You need to lift it 1 meter up. How much work does it take just to grab this box and lift it up 1 meter? Well, we know work is force times distance. The force that you're working against here is gravity of 100 newtons. And the distance we go is 1 meter. So our work is 100 joules. So the simple act of actually physically lifting the box without a pulley or something, this is called your work out. And sometimes it's denoted W with a little O, work out, which is 100 joules of energy. So that's how much work it requires you to lift a 100 newton or a 10 kilogram box up 1 meter. So now it says you rig up a pulley, and you don't actually do this. You don't actually lift it the 1 meter. You rig up a pulley instead because you don't want to expend that much force, 100 force. The pulley makes it 50 newtons of force to start moving the box. So this time it's less force. It's not 100 force newtons. It's going to be just 50 newtons because you made a pulley, which makes it easier. The rope needs to pull for 2 meters though. So you actually have to physically pull the rope for 2 meters worth of pulling. The thing to note is here, the box still goes up only 1 meter. You're pulling the rope for 2 meters, but it only goes up 1 meter. So your pulley might look like something like this, or like this. Where you're pulling up here, the rope you have to pull for 2 meters, and this will only go up 1 meter. So let's find out how much work you do on the rope. So it's again force times distance, and this time you're only doing 50 newtons of work, but your distance you go is 2 meters this time. So let's find out what the work is. It'll end up being 50 times 2, which is 100 joules, which is the same as there. This is called the work that you actually do. It's called the work in. And we do a little I there, which means work in. Okay, that's the work that you put in This is the work that the load or the box does work out. So if you notice, they're the same in this example, and this tells us essentially that maybe, I'm thinking, the simple machines, the work will always be the same. Maybe they'll always be the same. So if you make it easier, you're going to have to pull for longer. Okay, but generally it's not exactly true. They're not always the same. But you can think of this, if your simple machine efficiency is 100%. If it's 100% efficient, then they'll always be the same amount of work. Okay, so if your machine is 100% efficient, they should always equal the same amount. Okay, so if you make it easier, that means you're going to have to pull for that much longer. Okay, but they're still important because you can actually pull or lift something that's, say, at 500 kilograms. If something is 500 kilograms, you wouldn't be able to lift it. You could still do that amount of work if you make it lighter. That's why they're important. So you would say that the mechanical advantage of this pulley here is 2. Okay, this is what we're going to be going through and practicing, is mechanical advantage and efficiency. So you would say that the mechanical advantage of this is 2. And how you actually look at that is you look at the force values. It took 100 newtons of force to lift it 1 meter. So the force of gravity on this box is 100 newtons, but you, using the machine, only had to expend 50 over a longer period, but only 50. So how you find mechanical advantage is you usually just go this force divided by this force. 100 divided by 50, and that's how I got my 2 there. Okay. And if your work in and your work out are the same, that means it's going to be 100% efficient. Okay. If it takes more work here, more work in, your efficiency value will go down. Okay, this value will never be more than this value though. Okay, the max that the work in can be is 100 joules. It can't go, or the minimum that it can be is 100 joules. It can't be less than 100 joules because that's what our work out is. Okay, all right, so let's go over mechanical advantage. It's called mechanical advantage is load over effort force. And load just means the force of gravity of an object. And notice how it's force. It's not work. It's not work over work. It's a force over a force. And effort force is the force required to move it. So in our example here, again, we will go MA is our load, which is the force of gravity of the box, 100 newtons. And our effort force was 50 newtons right here, 50. And if you notice, we can cross off the units. Newtons and newtons cross off, and so we just get 100 divided by 50, which is 2. Notice how I don't put any units, because it's actually, mechanical advantage is unitless. It just means 2, which means 2 times easier to lift. But you got to lift for longer. That's one thing to remember. Alright, so let's go on to the next page, and this one looks at a lever. So it's the same idea, where you have a pulley where you're lifting something a certain amount, where it's going to go, maybe for this example, it's going to go up 1 meter, and it weighs, again, 100 newtons, so it's probably around 10 kilograms. But here, you're 3 meters from the fulcrum, so that means you are pulling 3 times, because this is only 1 meter from the fulcrum on this side. That means if it goes up 1 meter, you have to pull down 3 meters worth on the other side because it's 3 times further from the fulcrum. So it says you end up putting in 40 newtons of force downward. So not the 100 newtons, so it does make it easier. So we have some sort of mechanical advantage here. It's saying, what is the work in? Again, it's the work that you're putting into the machine. So it's this side here, work in. And then this side here is our work out. Okay, it's the work that the load does. So our work in is just force times distance. What force? This force times this distance. So it's going to be 40 times the distance of 3 meters. So it's going to be 120 joules, because it's work, of energy you put into this machine, into this lever down here. Now let's look at what the workout is. Our workout is, again, force times distance, which is going to be 100 newtons is the load kind of weight, and it only goes 1 meter. That's the overall distance it goes, so it's going to end up being 100 joules. So this is a more real-life example. Our last example, we had them both the same values, but this is more real life because nothing is really 100% efficient. So our work in is 120 joules, and our workout is 100 joules. All right, so it's saying what is the mechanical advantage? We have a formula for that, and you can put it on your formula sheet. It's load over effort. So what is our load force? Not the work value, but the force value. The load was 100 newtons, and our effort was 40. So overall, our mechanical advantage was 2.5, which means 2.5 times easier to lift. Note that it was not 3 times easier. It wasn't the same as the length. It was just 2.5 times easier. And then here, I don't know why there's a P there, but what is the efficiency? E. So E, if you can look just a little bit lower, we have a formula there for it. Your efficiency you can actually find if you have your work value. So you can just go work out over work in, and then times by 100% to get what your efficiency is. So our workout we already found was 100 joules. That's how much work the load actually did. Work in was this, how much we pushed down on this lever to lift it up that 1 meter. We put 120 joules in. That's the work in that we did. So we end up getting 0.83 repeating. And then what you do with efficiency is when you get this decimal value, you times by 100% to get a percent value. And then this will give us 83.3 repeating percent. So this lever is 83.3% efficient. Okay, so whatever energy we put in this, we're going to be losing kind of that 16%. Okay, so we can write this means 100 minus this value is how much energy we lost. So it's 16.6 repeating percent was lost to friction. So no matter how much energy we put into this machine, we're going to be losing 16.6% of that energy every time to lift anything. And this is because ideally our work in would equal our work out. That would make 100%. Alright, and this is one more thing to say. Work in is always greater than work out. You'll never have an instance where you put less work in than the load goes. Okay? And that's for any machine. Alright, that one's done. Last page, we're going to do sample questions here. Alright, what is the mechanical advantage of a pulley system if you can lift a 10 kilogram crate with a force of 25 newtons? Okay, so generally when I see a pulley question, you can see all these different pulleys here. We're not going to take into account how many there are. We're just going to say it's one pulley system with something you're lifting on one side and then your effort on the other side. So your work in this case, is on this side, and your box is on this side, work out. Okay, so let's calculate our values. We don't actually have to calculate for this question work in and work out. Generally, you always want to find out what work in and work out are, but it's saying what is the mechanical advantage? So we're going to have to use this equation, is load over effort. Our load force is, let's see, 10 kilogram crate. We don't want kilograms, we want a force, so it's going to be 10 times 9.81. Oh, I'm off the page, sorry. 10 times 9.81. And then our effort is, it says, is only 25 newtons. So overall it's 98.1 divided by 25, and we get around 3.92 as our mechanical advantage. So this one, generally with pulleys, the more pulleys you have, the higher the mechanical advantage goes. You have to pull for a lot longer, but it's a lot easier. So it's around 3.92 times easier to lift this mass, whatever it is, or 10 kilograms in this case. Now let's go into this question. It's saying a worker is testing a multiple pulley system just like this to estimate the heaviest object he could lift. So again, you have this box, goes over this pulley system, and you pull down. So you have a work-in value and a work-out. So let's find out what these are. Saying the largest force he could muster is 875 newtons. So he's pulling that, so that's the work-in force that he's doing. So the force that he's doing is 875 newtons. He says when he moves the rope 1.5 meters, so he's moving it, so that's the distance he goes. The object moves 0.25 meters, so that's going to be this distance over here, 0.25. It says what's the heaviest object you can lift. So we have these two kind of values. The work in we can calculate is 1312.5 joules of energy. And then this one we don't know the force of the box, or we don't know the mass of the box. That's what we're trying to find, so we're going to leave it. So for this question, we'll say, well, if 100% efficient, work in would equal work out. And again, work in is 1312.5. Our work out is force times 0.25. And so if we divide by 0.25, we get a force of 5250 Newton object. So that's how much weight this object has. You could always find the mass if you were curious, because force is mass times acceleration, which is 9.81. And then we divide by 9.81 and we get mass of 535 kilograms. So he can lift that with this pulley. All right, question number 3. Same sort of example. You have a pulley, you have a box, and you're going over this pulley system. All right, so here it's saying that your work in is going to be 180 joules to lift up this box, only 10 centimeters or 0.1 meters high. Okay, so not very high. And it says the object weighs 152 kilograms. So let's find out work out. Force times distance. This is going to be 152 times 9.81. Again, you can't see this, sorry. Is our force, because we have to go mass times acceleration, times our distance, which is 0.1 meters, and this will give us 149 joules. So we see that we put 180 joules of energy in, and we get out 149. So it's saying, 1, what is the efficiency? Efficiency is work out over work in, which is going to be 149 joules over 180 joules times 100%. And this gives us 82.7% efficiency for this pulley. Question 2. What is the mechanical advantage of the system if it takes 800 newtons to lift? Mechanical advantage is load over effort. And so this load is 152 times 9.81, because it's our mass times our acceleration of the box. And then our effort that we pull is 800, it says. 800 newtons to lift. So overall, this is going to be 1.86, which means 1.6 times easier to lift. All right, and then question 3 says, how many pulleys would you guess this have? The answer is 1 movable pulley, but we're not going to go into this today. So that one you can kind of disregard, but that's the answer for it. Thank you.